Here we go, Ignite students. It's time for a little review. We are going to kind of wrap up this beginning astronomy, motion of the moon, seasons, motion around Earth, and history. And we're going to have a quick assessment Monday, short test, and that way we can get into some of the big stuff, some light and radiation issues after that. But we're going to have an exam Monday on Canvas, kind of similar format to the last one. It shouldn't be very long. It'll be good. So use this as a review, and we'll go through some of the things you need to be ready for Monday. Let's look at some of the big ones. Motion of the moon. Here's a couple things. This image is kind of nice. All right, so the sun is on the left here, way off to your left. All right, it's not right here where the arrows are. It's way off screen, okay? And a couple things you can notice. In each image, the moon is half lit and half shaded. Don't look at the pictures around the outside. Look at the interior moon. Half the moon is lit, half the moon is shaded. Okay, dark side of the moon is a phrase that is always misinterpreted. It's a great Pink Floyd album, but beyond that, it's a phrase that is odd or wrong or means different things. Okay, the moon rotates. The moon sees the sun. All of the moon at some point in time gets sunlight. But the moon rotates on its axis at exactly the same rate as it revolves around the Earth. So only one side of the moon faces Earth. Only one side of the moon faces Earth. Any person who has ever been alive, say the 13 Apollo astronauts, okay, has only seen one side of the moon. Ancients, modern, telescope, doesn't matter. Only one side of the moon can you see from Earth. So unless you're in a spacecraft going around the backside, or you're looking at an image from a satellite that was sent to orbit the moon, you have not seen the far side of the moon. And sometimes people mistakenly say far side versus dark side, and they kind of mean different things. All of the moon turns, and all of the moon will get light, but the far side of the moon is dark, meaning that we're ignorant of it. We don't know about it until modern satellites and the space program, right? There was only one side of the moon that everybody knew and saw. It's the same side. Okay. Thing two. So, if the side of the moon facing Earth is dark, nothing's visible. If the side of the moon facing Earth is bright, it's a full moon. It's completely visible. Here, what's facing Earth? Well, half the moon is lit, half the moon is dark. Same thing down here. So, remember, Earth is turning, this is the North Pole. Earth is turning this way every 24 hours. The moon is going to take 29 and a half days to do this orbit. And the sun's still over here, and then the Earth is also going this way around the sun, but that's slower than these other two. Start with the new moon. Waxing crescents on the right side, it's less than half. First quarter is exactly half, and it's on the right. Waxing gibbous, it's bigger than half, but it's not full. Full. Waning gibbous, this picture is a little deceptive. I wish I'd taken it a day later. You could see that there's some shadow over here. Third quarter, up here at the top, if I don't move the mouse there, you could see it better at the top. And then waning gibbous, and what is visible is on the left-hand side. It's leftovers after the full moon. This is on the right. It's right before the full moon, and this is leftovers after the full moon. You need to know where all of these names go in this. All right, this is from an old textbook. You probably don't have access to that, or I know you don't. So this is in the OpenStax book. Flip everything around and put the sun way over here. Why is this a new moon? Because these outside ring is what you would see in the sky. right? And remember that the moon, I'm trying to show here, the moon is tilted in its orbit. So this is not exactly flat. There's not a shadow of the Earth going to be in an eclipse here. It's up a little or it's down a little. Same thing. We're not worried about that detail. So it's new moon. It's going around first quarter, or waxing crescent first quarter, waxing gibbous full, waning third quarter, waning new. It's all going around counterclockwise. Earth is turning, in this case, counterclockwise, and then the Earth is going around the sun. It would be coming towards you, down and out of the screen and around the sun this way. Okay. Same picture. This is in the OpenStax book. You've got access to that. Now, PhET, PhET, is an incredible resource that we haven't even mentioned yet. PhET's awesome. I'm going to run through several of them. It's going to really help you because, in addition, don't forget the history, big history, all that stuff from last week, motions of the moon, parallax, and observing. Those are things to think about. All right, here we go. This one, PhET, P-H-E-T, the University of Colorado Boulder. After one of the professors won the Nobel Prize, he used some of the prize money and created this thing. So there's all these cool simulations online from a really smart guy who created this like mini company or organization at UC Boulder to build all these things. This one, you can think of it as gravity. This one's about a game. This one's landing a little thing. No big deal. And I'll send you the link and you can get to all of these. Okay, the next two are gravity. We haven't talked about this. Newton's law of gravity much. The bigger things are, the more attracted, the more force they have between each other. And the closer they are, the more force they have between each other. Gravity is weak. Think of it this way. If you drop your pencil, it takes the entire mass of Earth to pull that pencil down. Right? If I drop a paper clip, a little bitty refrigerator magnet could go over and lift that paper clip up, even when all the mass of Earth is using gravity to pull it down. Gravity is weak compared to the other forces. But in space, it's kind of all there is. Like there's radiation, there's other things. It wins on big scales because it just keeps adding and adding and adding. Gravity wins at long scales. So take these guys. There you go. So the force arrow gets stronger. You got to pull. Hey, if I make this sphere heavier, 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 the forces get bigger and bigger and bigger. Okay? And we can make the balls constant size even though they're getting heavier. All right? Or make that one bigger and then they're leaning in. But the truth is, this is 0.00005 newtons. That's like less than feather. Like if you held a feather in your hand, it would put more force on your hand than that because gravity is weak. So what they do over here, they did the exact same thing, except this is now billions of kilograms and this is billions of kilograms. And so this is like a normal pull amount if you were actually pulling on this. So let's shrink these down so we can get it closer. And then let's just crank that mass up. And now they've got to lean back and pull against it. So the heavier these are, the stronger the force of gravity. The closer they are, the stronger the force of gravity. And you can work out all of these different examples. All right? Now, that's Newton's law of gravity. Easy enough. We have two different ones about orbits we're going to look at real fast. So, phet.colorado.edu. I'll show you where to get the specific ones we're going to load up. Okay? All right. Model. We'll start with the model, and then we'll put it to scale. I can do the sun and the earth, sun, the earth, and the moon, earth and moon, or earth and a satellite. Let's just start here and hit play. And then we'll put it in fast forward. And I could show you the force of gravity. Oh, gravity's pulling Earth towards the sun, but it's also pulling sun towards Earth. Newton's third law, equal and opposite reactions. For every action, there's an equal. So if sun pulls on Earth, Earth pulls on the sun. Hey, the sun, Earth is actually moving this way. It's trying to go this way, but gravity's pulling it in, and it's turning. You could come down here and you could increase the mass of the sun and watch all of a sudden, wham. Okay, that didn't work well. Reset this. Okay, you could show the path. That's maybe better. We don't have to show the velocity or the gravity force. You just show the path, and then as you increase the mass of the sun, things don't go well, right? Reset that. Now check this out. Remember Ptolemy, Ptolemy, in the history lesson when we talked about the spirograph, circles on circles on circles? If you actually graph the position of the moon, it's going around the sun. You've got to look the Earth. The moon is going around the Earth. You have to look really closely because otherwise it does not look like a circle around the Earth. But it does look like that spirograph going around the middle. And that's how Ptolemy was able to make those wrong models actually work, is he made lots of this. Now we can change the mass of Earth and things will start to, now the moon's not as attracted to Earth. The moon's more attracted to the sun, and Earth is going to spiral out. Moon, it was headed into the Earth. We're in fast forward, and the moon may hit a stable orbit there. There we go. Not quite stable. Because it's attracted to Earth. So every time Earth comes around, it gets pulled out a little. And then as it gets away from Earth, it's going to dive in. It's opposite of Earth. It's going to be over here. And now as it's going to come close to Earth, it's going to swing wide. There we go. And Earth's going to slow it down. And all sorts of craziness. You could play with this. The whole point is that you get to manipulate these things and change them. All right, if we just want to look at the Earth and the moon, easy enough. Hey, wait, why does the Earth look like it's moving? Because it does. Remember we had the long stick and the bar in the middle, and then both things moved around the stick? That's what's going on here. And Earth and a satellite, you could change the mass of Earth, and it gets bad real fast. Let's reset these, and instead of model down here, click on scale. Oh, no, reset, so it's back to this. Hit to scale. To scale, that's the sun, Earth, and, this one. There's the moon going around Earth compared to sun. All right, we can even show the velocities of both the moon and the... Space is big. Space is really big, okay? So you could play with these, increase the mass of the star, and watch how all of a sudden it's not going to hit there. You could put a grid up so you could see how it's shrinking. You could get all sorts of stuff going on. The moon's going to leave us. No, it's not. The sun's going to help. It's going to come back and cut on the inside here. Nope. This is just playing around. You're learning. I do want you to look through these. There'll be a super short assignment just to show me that you looked at these when you did the review. Just look through some stuff, take a screenshot, and submit it. It'll be on Canvas, the instructions. Last one. This one. My solar system. I forgot. We're going to allow it. We're going to let it go because it's in a browser. Okay, we're going to let it go. This, you can do whole solar systems that don't even exist. So this is just a planet and a star. So body 1, body 2, you can create 3 bodies and watch this. And you can watch cool spirograph stuff. If you just let this one go for a while, the picture is actually kind of pretty. All right. But this is a moon, which is actually circling this. And remember, the sun, I'm pointing here, the sun in the middle actually is making small orbits. And so it does come back around. You can show the traces. We could show a grid. Let's get rid of that. We could have a tape measure. We don't need that. You can't really change these masses and initial positions, but you could do other things. And then it nearly finishes. It doesn't reconnect the first time it goes past. It's not an even interval, so we're not going to wait for that to finish. 4 things going on. This guy's just going to do its own thing, and these 2 are going to orbit. His orbit will get closer and further depending on where the sun is around its loop and where these guys are on their loops. All that's fine. Look over here, the presets. Sun and planet, moon. Binary stars? That's 2 stars. So, 2 stars, yellow and pink, and a blue planet that would be doing this. Usually the planet would not be in between, but you get all sorts of crazy stuff. All right? 4-star Ballet. This one is everybody's even, everybody's lined up, and they set it up to do something really interesting. Whoa. The orbits, they slow down on the outside, slow down, speed up as they all go towards their own middles. If you remember, I talked about Kepler's law, the equal area and equal time. This shows exactly they slow down on the outside, and then as they come back to the middle, you can see them speed up and whip around and go again. Okay? Slingshots and double slingshots. So these guys are all going to try and orbit, but it gets close to that one, and the gravity, it got close enough. This little blue guy is going to get close enough to the purple one on this lap that the gravity from the purple one's going to fling it up and out. NASA uses this gravity slingshot with spacecraft all the time to speed them up, slow them down. All right, we can get, so it gets shot by the purple and the blue. All right, and that's how we can get spacecraft to speed up and go way out just like that. There's a couple more, double, hyperbolic, ellipses. Here we go. This is Kepler's law. Planets orbit in ellipses, and this just has 3 nice ellipses shown up. Watch the green one. Slow down, make the turn, but there's a lot of mass here. Gravity's going to pull it in. It's going to pull it in. It's going to pull it in, and then it's going to whip around the corner, and then gravity's pulling it here. It's going to slow it down, turn it around, speed it up, and it's going to drop in and go. Okay. That's been part of the review. These are fun to look at. Focus on this, your vocabulary, your history, know about some different things. Do the quick assignment review, test Monday. Term ends Friday, tomorrow. Everybody have a good week.